In the previous lesson, we talked about the concept of unit analysis and how to manipulate the units in order to find an equivalence between two different units. So in this lesson, we are going to build on what we learned in the previous section and apply unit analysis to real-world scenarios. So one thing to keep in mind while we walk through the lesson together is that unit analysis isn't a theoretical concept. What we're looking at is an actual tool that helps us solve problems in a lot of different areas, especially the sciences and chemistry, physics, all that kind of stuff. But we can use it in our everyday life as well. So keep in mind that this is a tool that you can keep in your toolbox and then pull it out when you need it. So this first example here, we're going to apply it to length. So we have that the length of a Kentucky Derby horse race is 10 furlongs. How long is the race in miles? So this is an unusual unit. I haven't really seen it anywhere other than horse races. But if we want to change 10 furlongs into miles, we need to know what the conversion factor is. And our conversion factor is that 1 furlong is equivalent to 0.125 miles. And this information you can get on the reference sheet that I posted in the introductory module. Now, there are two ways that we can write that equivalence. We can put furlong on the top and miles on the bottom, or the other way around, where we put miles on the top and furlong in the bottom. But either way, both of these fractions are equal to 1 because the top and the bottom are equivalent. So we're going to start with what we're trying to change. We have 10 furlongs and we want to change it into miles. So we start with 10 furlongs and I put that over 1. And then I need to multiply by one of these two factors, and I determine which factor it is by looking to see what I want to cancel out. Since I want to get rid of furlongs, then I want the furlong to be on the bottom. You should have it on opposite sides of the fraction bar. So furlongs are going to go on the bottom and then miles on the top. Then I can cancel out the furlongs, and then all I would have to do is multiply it across the top and across the bottom. Or you can just set it up as individual fractions and multiply. So we would end up taking 10 times 0.125, which is 1.25. And then 1 times 1 on the bottom is 1. And then when I take 1.25 miles and divide it by 1, it's the same thing. We get 1.25 miles. And I know that my units are correct because I crossed off the furlongs and miles is what I'm left with. So we changed furlongs into miles. So in this example, we're going to talk about a price comparison. When you are making a price comparison, you want to make sure that whatever the two things are that you're comparing are in the same unit. In other words, for example, in this problem, it says you have something in ounces and something in pounds. If they're both in pounds or if they're both in ounces, it makes it easier to compare. It's also easier when you determine what's called the unit price. And the unit price is the cost per unit. So if something is in pounds, that means we would determine what the cost is for each pound. Or if something's in gallons, we would determine the cost for each gallon. We would break it down into one unit of whatever it is. That also makes it easier to compare. So in this example, it says you're planning to make pesto and you need to buy basil. And you have two options. The grocery store sells small containers of basil at $2.99 for each container, and each container has 2/3 ounces. Then you also know that there's a farmer's market going on downtown this week, and you can buy basil in bunches for $12 a pound. Which one is the better deal? So at first glance, it might look like the basil in the containers are a better price because you see $2.99, and then for the bunches, you see $12 per pound. So when you look at those numbers right off, it looks like the containers would be the better deal. But because the containers are in ounces versus the bunches are in pounds, we need to put them in the same unit to compare. And we want to put them in terms of the unit price. That makes it even easier to compare. The basil that's in bunches is already in that format of unit price because it states here that it's $12 per pound. So we know how much it is exactly for each pound. So that's already in unit price format. But we need to look at $2.99 for each 2/3 ounce container. So what I'm going to do is I'm going to take the ounces and convert it to pounds. So for each container, it's $2.99, and that's for 2/3 ounce. So we're going to put $2.99, the word per means to divide, and then underneath we're going to put 2/3 ounce. I want to change this to pounds, so you should look up on your reference sheet how many ounces are in a pound, and you will find that there's 16 ounces in a pound. Because I want the ounces to cancel and I want to be left with pounds in the denominator, I'm going to put the ounces on top and the 1 pound on the bottom. Then when I multiply, the ounces drop out and I'm left with this unit here, which is the price, and then this unit here, which is pounds. So that would be price per pound. What I have to do now is just do the arithmetic. So across the top, I'm going to do 2.99 times 16. And then across the bottom, I'm going to do 2/3 times 1, and then simplify. When you work that out, you're going to find that if we put it in terms of pound, those containers would cost $71.76, almost $72 a pound for the basil in those containers. Where if we buy it in bunches, for 1 pound, it would cost $12. So when you buy it in the containers, that's 6 times as much as the farmer's market price. So I would personally go to the farmer's market to get my basil. We are now going to talk about some examples in the metric system. So first, let's talk a little bit about the metric system. And most people in the US struggle with the metric system because we're so used to using what we use. But in reality, the metric system is so much easier. The reason that the metric system is so much easier is because they only have 4 units. They have one for length, which is the meter. They have one for mass, which is kilogram, one for time, which is the seconds, and then they have liters for volume. Those are the only 4 units they use. And then they use factors of 10 to show how big or small the meter is. So the metric system is based on factors of 10. Instead of worrying about, 2.35 of this is equal to 1.78 of this, it's all based on tens. So that makes everything so much easier because it follows the same pattern no matter what unit you're using. So here, the breakdown of the most common prefixes. The prefix is based on the factor of 10. When you put a prefix in front of one of the units, that is what helps determine how big or small it is. So when you look at this table, we have deci, and deci means 1/10 of whatever unit you're using. So for example, if we're talking about meters, if I put deci in front of meters, that would mean it's 1/10 of a meter. If I put centi in front of meters, that would be 1/100th of a meter. And that follows the same rules as far as grams. If I put deci in front of grams and called it decigrams, that means decigrams is 1/10 of a gram. If I put milli in front of grams, that means it's 1/1000th of a gram. I could use it for liters. If I said milliliter, that means it's 1/1000 of a liter. So it always follows the same pattern. And you just use these prefixes here and here to determine how big or small it is when you're comparing it to the main unit. So in this table here, these are the smaller values. This is when you're going to be less than 1 unit. So less than a meter or less than a liter, less than a gram. Okay. So these are the smaller values. These are the larger values over here where it's going to be greater than 1 unit. So if I had a decagram, that would be 10 grams because it's 10 times 1 gram. If I use kilogram, that means it's 10 to the third, which means it's 1,000 grams. So these prefixes here tell us exactly how big or small that main unit is. Let's look at the first example. I would definitely have your reference sheet in front of you while you're working through your homework, unless, of course, you're already very familiar with the metric system. But if you're not, you're going to need to look up what the prefixes mean until you get the hang of it and become familiar with it. Using metric prefixes, it says convert 2,759 centimeters to meters. So this is what we're trying to convert to meters. So we're going to start with 2,759 centimeters and put that over 1. If I want to change from centimeters to meters, if we go back up to that table and look at the prefix for centi. So a centimeter is 1/100th of a meter. Or another way you can say that is there are 100 centimeters in 1 meter. Since I want to cross off the centimeters, I want to put the centimeters for our conversion factor in the denominator. So I'm going to write 1 meter on top is equivalent to 100 centimeters, which is in the denominator. So I cross off my centimeters and I just take 2,759 times 1. And then on the bottom, I have 1 times 100. So that means I'm basically going to take 2,759 and divide it by 100. Because it's based on base 10, really what you're just doing is moving the decimal place. Because we're dividing by 100 and making the value smaller because we're dividing, then we're going to move the decimal 2 places to the left. So instead of having here at 2,759 centimeters, we're going to move it over 2 places this way and have 27.59 meters. Looking at this example here, it says the marathon running race is about 26.2 miles. About how far is it in kilometers? This is an example where we are crossing over from system to system. So we're using miles, which is the US system, and then we're changing it to the metric system. When you are crossing over from one system to another, no matter which direction you're going, there's a table in your reference sheet that gives you some units to do that. So you want to look, since this is in terms of length, because we're talking about miles and kilometers, you want to look at that table and you want to look at one of the conversion factors that goes back and forth using length. So one of the things that you'll find on there is that 1.6093 kilometers is equal to 1 mile. Since we want to cancel out the miles, I'm going to put the miles on the bottom. And then when we go across the top and across the bottom and we simplify, since miles are canceled out, we're left with kilometers. And then when we work out the arithmetic, we're going to get 42.2 kilometers. When we talk about Unix and temperature, the Unix that we typically use in the US is Fahrenheit. And that's where water freezes at 32 degrees, and that's in Fahrenheit, and then boils at 212 degrees Fahrenheit. In most other countries, Celsius is used, and that is where water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. And you can see when we line them up here how they compare. So here's Celsius and here's Fahrenheit. When we look at the freezing, here it says water freezes. That would be at 0 degrees Celsius and 32 degrees Fahrenheit. when we look at this, where the water boils, when we come across here, that's 100 degrees Celsius, and in Fahrenheit, it would be 212. So these are the temperature systems that we're familiar with, although we're more familiar with Fahrenheit, but most of us have heard of Celsius. One temperature system that you may not have heard of is called Kelvin. So the Kelvin scale is going to start at what's called absolute zero. And Kelvin is usually only used by scientists because they include that absolute zero on their scale. That's where it starts at 0 Kelvin. And absolute zero is when the molecules in an object completely ceases to move around, or at least theoretically. That is why the Kelvin system is used mainly in science disciplines. Another thing to notice is that Kelvin doesn't have negative degrees because 0 Kelvin starts at absolute zero. And one other thing to notice is that when we use Fahrenheit and Celsius, we use that little degree symbol and then we put an F or a C with it to determine which system we're using. In Kelvin, we don't use degrees, we just stick a K in front of it. So that's another thing to notice. So here are your formulas for temperature conversions. So if you want to convert Celsius to Fahrenheit, you want to use this formula. So you would plug in your degrees of Celsius, multiply it by 1.8, and then add 32. If you want to go from Fahrenheit to Celsius, then you want to use this formula where you plug in Fahrenheit, subtract 32, and then take that answer and divide by 1.8. These two equations here are the same exact equation. They're just rearranged differently. Now down here, formulas involving Kelvin, we don't have formulas to go back and forth between Kelvin and Fahrenheit. We only have the formulas for Celsius and Kelvin. So if we want to go between Kelvin and Fahrenheit or in the other direction, we're going to have to make two steps. So for example, if I want to go from Fahrenheit to Kelvin, I first need to change Fahrenheit to Celsius, and then I change Celsius to Kelvin. Or if I want to go from Kelvin to Fahrenheit, then I need to change Kelvin into Celsius, and then use this to go from Celsius to Fahrenheit. So there's a direct relationship here between Celsius and Kelvin, but not between Fahrenheit and Kelvin. Actually, let me restate that. There is a relationship between Fahrenheit and Kelvin. We just don't have that formula in this table. And it would be actually a pretty good exercise for you guys to figure out how to use these formulas in the table to create a relationship between Fahrenheit and Kelvin. So here are your formulas here for the relationship between Celsius and Kelvin. Let's start looking at some examples. It says human body temperature. The average human body temperature is 98.6 Fahrenheit. What is it in Celsius and what is it in Kelvin? So using the formula that was given to us in the previous slide on that chart, we want to go from Fahrenheit to Celsius. So since the temperature that we're trying to convert is 98.6, I'm going to take 98.6 Fahrenheit and plug it in for F, and then I'm going to work out the arithmetic, and then I'll get out Celsius. So the average human body temperature in Celsius would be 37 degrees Celsius. Now, if you want to go from Fahrenheit to Kelvin, we have to make an extra step. We already have the Celsius, so then we can just take this and plug it into our Kelvin formula. So I'm going to take 37 and plug it into our Celsius. And our Kelvin equation is when you take your Celsius and you add it to 273.15. So all I have to do is take 37 and add it to 273.15, and we get 310.15 Kelvin. Notice there's no degree sign, it's just K. The next topic in our lesson, we're going to talk about energy and power, and then the units that go along with that. Energy is what makes matter move or heat up, and we use the unit joule for that. Power is the rate in which energy is used. So we have the joule, that's for energy, and then we have the rate in which it's used, so it's going to be joule over a period of time. You're comparing that unit over a certain time frame. So if we think about traveling, let's say 50 miles. If we talk about traveling 50 miles, but then we talk about 50 miles over a time frame, so we would say 50 miles, say, per hour, that speed is the rate in which you are covering that distance. It's the rate in which you're moving. So we have the distance and then the rate of the distance. That's the same idea here. We have energy, and then the rate of the energy is the power. Now, there are two ways that we can write power in terms of units. We have watt, that's a way to measure the rate at which the energy is used. And then because power is the rate of energy, you can also say it as joule per second. So when we use 1 joule in a second, that's the rate in which we use energy, which is equivalent to 1 watt. When we talk about a kilowatt hour, that's also a unit of energy, but we take the kilowatts and we multiply it by the hour. And that's what that hyphen means. A lot of times that hyphen in mathematics means multiplication. Here's another conversion factor that you're going to need to use. 1 kilowatt hour is equal to 3.6 million joules. Another thing to remember or recognize is that kilo means 1,000. And so that means if I have 1,000 watts, that will be the same as saying 1 kilowatt. Now that we have the idea of power and energy, let's work through an example about finding the cost to use a light bulb. It says a utility company charges 15 cents per kilowatt hour of electricity. How much does it cost to keep a 100-watt light bulb on for a week? So in order to find the cost of running a 100-watt light bulb for a week, we need to determine the amount of energy used, because cost is determined by the amount of energy. And we also need to take into consideration that we're thinking about this in terms of a week. To find kilowatt hours, we need to find kilowatts and multiply it by the number of hours. Once we know what kilowatt hours are, all we have to do is multiply by 15 cents and we'll have the cost. So our strategy here is to use the watts, change it into kilowatt hours, and then use the kilowatt hours to multiply by the 15 cents and find the cost. Kilowatt hours is when you take the kilowatts and multiply it by the number of hours used. We know that we're going to use it for a week, so one thing we need to do is change a week into hours. Because we're given watts and we need to know kilowatt, we also need to translate watts into kilowatts. Let's first start with watts. I know that kilo means 1,000. So there's 1,000 watts in 1 kilowatt. So since I want to get rid of the watts and end up with kilowatts, I'm going to put 1,000 watts in the denominator, and then 1 kilowatt is going to go in the numerator. So this is our conversion factor. 1 kilowatt is equal to 1,000 watts. When I cross off watts here, that will leave me with kilowatts, which is part of what we need to know. We need to determine kilowatt hours so that we can multiply it by 15 cents. So now what we need to do, we know that we're doing this for a week, but we need to figure it out in hours. So I'm going to multiply by 1 week, but then I'm going to translate that into hours. So I'm going to use my conversion factors here to translate into hours. Once I do that, what I'm left with, once I cancel everything out, I'm left with kilowatt times hours, which is exactly what we need to find. We need to find kilowatt hours. So when I work this arithmetic out, I'm going to get 16.8 kilowatt hours. All the other units are canceled except for kilowatt and times hours. So now we have our kilowatt hours. So what we're going to do now is take the kilowatt hours and multiply it by 15 cents per kilowatt hour. So now the kilowatt hours cancel, and all I'm left with is the amount of money in cents so far. So if I take 16.8 kilowatts and I multiply by 15 cents, the kilowatt hours cancel, and I would be left with 2.52 cents. If you want to change that in dollars, instead of having 252 cents, then I could use this conversion factor that I know there's 100 cents and $1. So now I can cross off the cents, so I have my answer in terms of dollars. So $2.52 is what it costs to run this light bulb, 100-watt light bulb, for 1 week. Now in part B, it says, how much will you save in a year if you replace the light bulb with an LED light bulb that provides the same amount of light but only use 25 watts of power? So up here we have 100 watts. Down here we have 25 watts. So all you have to do is walk through the same exact process, but instead of starting off with 100 watts, we're going to start off with 25 watts. So I just switched that out from 100 watts to 25 watts, and I'm going to go through the same process. What I'm going to find is at the end of the week, I would have used 4.2 kilowatt hours. If I find the amount of money that it costs to run 4.2 kilowatt hours for a week, I have to take the 4.2 kilowatt hours and multiply it by 15 cents. And then again, you can translate it into dollars by using the conversion factor that $1 is equal to 100 cents. And that way the cents cancel. And now we can also cancel the kilowatt hours, and we're left with dollars. Now this is for a week. Remember, we did this in terms of a week. Same thing up here. Whoops, 252 for a week, and then down here, 63 cents for a week. So the question is asking how much would we save in a year? Since I know there are 52 weeks in a year, if I find the difference between this amount and this amount, and then I multiply it by 52 weeks, that would give me the amount I would save in a year. So when I take 252 per week and subtract 63 cents per week, that means I'm going to save $1.89 per week. Now I'm going to switch this from weeks into a year. So if I save $1.89 per week and I want to change weeks into years, I'm going to use the conversion factor that I know that there's 1 year is equivalent to 52 weeks. I'm going to put the 52 weeks in the numerator, so my weeks cross off, and then when I multiply this out, I'm going to get $98 per year. The answer is actually $98.28, but I just rounded it to the nearest dollar. Just keep in mind when you're working through your homework to pay attention to the directions on how you're supposed to round your values. Now we're going to talk about the last topic in this lesson. We're going to talk about the difference between density and concentration. So here's the definition for density. It says the amount of items in a specific area or volume. When you think about density, you should be thinking about how much stuff, whether it's people, things, air particles, how much stuff is packed into a specific area or volume. High density means that there's a lot of stuff stuffed into a small space, and then low density means there's less stuff spread out over a larger area or a larger volume. Looking at this first example here about density involving mass, if we consider a volume that's 1 cubic foot. And we have 2 blocks that are 1 cubic foot. One is wooden, and it has a mass of 10 kilograms. The other one is steel, but has a mass of 220 kilograms. The steel block is going to have a higher mass density because there's 220 kilograms packed into a cubic foot compared to the wooden block that has a density of 10 kilograms for 1 cubic foot. So there's more stuff packed into that steel block versus the wooden block. Looking at the second example of density, we're going to talk about an example for population. So imagine you have 2 cities. You have a city that has a population of 100,000 people, and the area of the city is 50 square miles. Then city B has the same population, but it's only in an area of 25 square miles. So city B would have a higher population density because it has the same number of people, but it is packed into a smaller area, which makes it more crowded. So this example is about an ear infection. And it says a child weighing 15 kilograms has a bacterial ear infection. A physician orders treatment with amoxicillin at a dosage based on 30 milligrams per kilogram of body weight. And the dosage is going to be every 12 hours. So our conversion factor that we're going to need to use here, remember conversion factors sets up an equivalence between 2 quantities. So the dosage is 30 milligrams for every kilogram of body weight, and the child weighs 15 kilograms. So using our conversion factor, I want to get rid of kilograms and keep the milligrams because we're trying to figure out the amount of amoxicillin that the child is going to get. So for every kilogram of his body weight, he gets 30 milligrams of medication. So when we cross off the kilograms, we're going to take 15 times 30, and we're going to get 225 milligrams of the antibiotic, and that's going to be every 12 hours. For part B, it says, if the medicine is to be taken in a liquid suspension with a concentration of 25 milligrams per milliliter, how much should the child take every 12 hours? So here's a concentration example where we have 2 things are being mixed. We have the suspension liquid, and then we have the amount of medication. So for every milliliter of the liquid, there's going to be 25 milligrams of the medication. We know that the child needs 225 milligrams every 12 hours. So we need to take 225 milligrams and change it into the amount of antibiotic in the suspension. So we're going to start with 225 milligrams and change that into the amount of liquid suspension. Our answer needs to be in milliliters because that's our units for the liquid. And we know that every milliliter, there's 25 milligrams. So I'm going to put milligrams on the bottom and cross that off. And then when those are crossed off, I'm left with milliliters. I could have put milliliters on the bottom and milligrams on top. However, that wouldn't get rid of the milligrams and leave us with the milliliters of liquid. So when I multiply these 2 fractions together and I do the arithmetic, I'm going to get that we have 9 milliliters of liquid suspension.